Right now, something from another star is inside our solar system. It is an interstellar visitor astronomers call 3I Atlas. In just days, fresh images have revealed a tail millions of miles long. Even stranger, a second tail appears to point back toward the sun instead of away from it. That should not happen if sunlight and solar wind are in control. Now experts are questioning the physics and even the nature of the object. Mystery indeed. If you want to follow this mystery, hit like, subscribe, and turn on notifications so you do not miss what comes next. So, what are we actually looking at? The newest images, taken from observatories in places like Spain and Chile, show a bright, swollen coma wrapped around the core of 3I Atlas and a vast ribbon of material streaming away into space. That main tail stretches for millions of kilometers, a structure so large that if it passed through the orbit of Earth, it would span the distance between our world and the Moon many times over. On its own, that would already make this one of the more spectacular comets we have ever seen. But the real trouble starts with the second feature in those images. Extending in almost the opposite direction is a sharp, needle-like structure that points back toward the sun. This is the so-called anti-tail. Under normal conditions, dust and gas are pushed away from the sun by light pressure and by the solar wind, a stream of charged particles racing outward at around 400 kilometers per second. Yet the anti-tail on 3I Atlas looks like a jet punching upstream into that flow, as if the comet is pushing harder than the star. When astronomers run the numbers on how dense that jet would need to be to stand its ground, the answer is shocking. The material has to behave as if it is roughly 1,000,000 times denser than the surrounding solar wind. That implies billions of tons of dust and gas being thrown off in only a few months. Perhaps around 10% of the entire object ripped away in one season near the sun. That is not normal, gentle outgassing. It is more like a controlled burn. At the same time, tracking data show that the orbit of 3I Atlas is not following a simple gravitational path. Tiny deviations are building up, hinting that those violent jets are acting like engines and giving the object an extra push. Put the 5 million-mile scale of the tail, the impossible-looking anti-tail, and the drifting trajectory together, and you get a question that keeps astronomers awake at night. Are we watching an extreme but natural comet die in real time, or something that was never just a comet in the first place? In the next part, we will slow down and unpack what tails are supposed to do, and why this one seems determined to break the rules. To understand why 3I Atlas is freaking people out, we need to start with a simple picture of what a comet is supposed to do. Take a dirty snowball of ice and dust, drop it into the inner solar system, and warm it with sunlight. Ice turns straight into gas, gas drags dust with it, and the whole cloud gets pushed away from the sun. You get a glowing head and one or two tails that stream outwards like hair in the wind. That is the textbook version. Classic comets usually show two main structures. One is a dust tail, broad and curved, made of tiny solid grains that reflect sunlight. The other is an ion tail, made of charged gas that glows and points almost exactly away from the sun, lined up with the solar wind. Both of these features obey the same basic rule. The star pushes and the comet yields. Light pressure and plasma outflow shove material downstream, away from the furnace at the center. 3I Atlas has the dust and ion tails, but on top of those it shows something much stranger. Images from late November reveal an enormous main tail stretching roughly 5 million kilometers away from the sun, plus a narrow spike of material pointing almost exactly toward it. This is the anti-tail, a structure that appears to defy the usual rule. Instead of being blown back, it looks like a spear thrust straight into the solar wind. Now, anti-tails are not unheard of. In some cases, they are tricks of perspective when we see a sheet of dust aligned edge on. But that explanation struggles with the sheer scale and sharpness of what we see here. To keep a sunward feature visible while plasma streams out from the star at hundreds of kilometers per second, the comet needs to be throwing material outward with incredible force. The ram pressure of that flow has to be vastly higher than the background solar wind by factors of hundreds of thousands or even 1,000,000. Translate that into mass and you get a brutal story. Over just a couple of months, the object may be shedding billions of tons of material, perhaps around a tenth of its entire mass, turning itself into a fog of dust and gas on a timescale that is shockingly short. Normally, comets erode over many passes near the sun. 3I Atlas looks like it is burning through its reserves in one furious act. So the question becomes simple and unsettling. What is driving this violence? Is it just sunlight hitting a cocktail of ultra-volatile ices that we rarely see? Or are we watching some deeper process that channels energy and matter in a far more organized way? In the next part, we will leave the glowing tails behind and follow the object orbit itself to see how invisible pushes are quietly bending its path through space. If tails are the special effects, the real plot twist is happening in the orbit. When astronomers talk about a comet path, they usually mean a curve carved out by gravity alone. The sun pulls, planets tug a little, and you can write down a neat equation that predicts where the object will be months or years from now. For most comets, the sky follows the math with beautiful obedience. 3I Atlas is not being obedient. As data has piled up, observers have noticed that the real positions of this object keep drifting away from the path that pure gravity predicts. At first, that could be noise, bad weather, small errors in timing, but the signal has grown. The latest analyses say the extra push is now detected at around 10 standard deviations, which in science speak means it is extremely unlikely to be a fluke. Something real is nudging this thing. The standard explanation is simple and clever. If a comet blasts gas and dust more strongly from one side than the other, those jets act like tiny rocket engines. Every grain of dust that flies off in one direction gives the nucleus a subtle kick in the opposite direction. Add those kicks up over weeks and months, and the entire orbit shifts. That is what we call non-gravitational acceleration. It is not magic. It is just Newtonian physics with a gas tank. The trouble once again lies in the numbers. To get the amount of acceleration astronomers are measuring for 3I Atlas, the jets have to be incredibly powerful and incredibly lopsided. The comet would need to throw away mass at a rate that lines up awkwardly with what we actually see in its brightness and tails. It is as if the visible exhaust and the invisible push do not quite balance out. That mismatch is what leads some researchers to quietly play with a more radical idea. If this were not just ice and rock, but some kind of engineered object, it would not need to throw away nearly as much mass to get the same push. Chemical rockets can fling exhaust faster than simple boiling ice. Ion drives go faster still, trading mass for efficiency. In those cases, a small amount of propellant can bend a path dramatically over time. To be clear, most astronomers still expect nature to win this argument. They point out that our models of interstellar comets are based on almost no data, and that weird behavior is exactly what we should expect from a tiny, biased sample. But even they admit that the combination of strong, non-gravitational acceleration, focused jets, and extreme mass loss makes 3I Atlas an outlier among outliers. So we are left with a strange picture. An object from another star, flinging material into space with almost violent intensity, and at the same time gliding along a path that refuses to be purely gravitational. In the next part, that path leads us toward a date with the largest planet in our system, and a question that sounds almost like science fiction. Did this visitor accidentally wander near Jupiter? Or is it on a precisely aimed approach to the giant world gravity well? Follow the path of 3I Atlas far enough into the future, and it does something no other interstellar visitor has ever done in our records. It heads straight toward the domain of Jupiter. Not toward a crash, but toward something almost as dramatic, the invisible bubble where Jupiter pulls harder than the Sun. That region has a name that sounds technical, the Hill radius, but the idea is simple. It is the zone, where Jupiter is the boss. Imagine the solar system as a giant dance floor. The Sun leads almost every partner, but around Jupiter there is a patch where its gravity takes over the steps. If you pass close enough to that patch, your orbit can be twisted, sped up, slowed down, or even captured for a while. On March 16, 2026, calculations say 3I Atlas will skim the edge of that Jovian bubble. For an object that started around another star, that is one remarkable meetup. Here's where the numbers start to whisper in a more unsettling way. Some teams find that they can predict this encounter to better than 4 significant digits in distance. In plainer language, after a journey that may have taken millions of years through interstellar space, through nudges from passing stars and clouds of gas, the object still arrives on a path that threads its way to Jupiter Hill radius with astonishing precision. You can look at that and shrug, Maybe this is what happens when you have enough comets and enough time. Some will always pass near a giant planet by chance. You can also look at it and feel a little chill. If you wanted to study a solar system, you might send probes to fly near the biggest planet, where gravity can bend their path and give them flexible routes to the rest of the system. The data alone cannot tell you whether this is coincidence or choreography, but the timing and geometry are hard to ignore. And then there is Juno. Right now, that spacecraft is looping around Jupiter, mapping its gravity, its auroras, and its deep interior. If mission planners can time it right, Juno might also get a chance to watch an interstellar visitor skim the edge of the planet gravity well. Tiny changes in the comet path, small shifts in its spin or brightness during the encounter, could reveal how mass is distributed inside and how rigid or fragile the nucleus really is. So this future brush with Jupiter is more than a cool orbital trick. It is a natural experiment set up for us by the dynamics of the solar system, a test that could either make 3I Atlas look more like a normal, though wild comet, or push it deeper into the realm of the strange. In the next part, we leave Jupiter in the future and race back to a closer date on our own calendars, the December window when Earth telescopes get their best look at this visitor before it heads toward that giant planet showdown. Before 3I Atlas flirts with Jupiter gravity, it first sweeps past us. On December 19, 2025, this object will slip to within about 269 million kilometers of Earth. In cosmic terms, that is not a near miss, but it is close enough for our best telescopes to turn this faint dot with a tail into a rich laboratory. For a few precious days, we sit in the perfect spot to interrogate a visitor from another star. Across the planet, observatories have circled that week in red. The Hubble Space Telescope is lining up its schedule. The James Webb Space Telescope, normally focused on the deep universe, is being asked to glance inward and look at something in our own neighborhood. Giant ground-based instruments in Hawaii, Chile, Europe, and elsewhere are reserving night after night of time. Even skilled amateurs with half-meter telescopes are practicing their tracking routines. It feels less like routine observing and more like a coordinated stakeout. The main weapon in this campaign is not just pretty pictures, but spectroscopy. When sunlight passes through the gas around the comet, or when that gas glows on its own, it leaves fingerprints in the light. By spreading that light into a rainbow and measuring the lines, astronomers can tell which molecules are present. Water vapor points toward familiar comet chemistry. Frozen nitrogen or carbon monoxide in large amounts would hint at something more extreme and more typical of deep interstellar cold. Strange emission patterns might even force brand new ideas. Speed is the other crucial clue. If sunlight is simply warming ices and letting them boil away, the gas should fly off at a few hundred meters per second. Chemical thrusters would throw material faster, ion engines faster still. By measuring how quickly the jets expand and how the non-gravitational acceleration responds over the weeks around closest approach, scientists can begin to test which picture fits and which fails. This is how you look for ghost engines without ever seeing hardware. There's also the hope of glimpsing the nucleus itself. At this distance, with the coma still blazing, it will not be easy. Yet with careful image processing and clever tricks, Hubble and other telescopes might be able to peer through the glow and tease out the shape of the solid body at the heart of the storm. If that shape looks like a lumpy, irregular shard of ice and rock, the natural comet story gets a boost. If it hints at symmetry or sharp geometry, the questions grow louder. All of this happens on a tight clock. The object is brightening, moving, changing as it races past. The December campaign is not just another observation run. It is our best, perhaps only, chance to ask hard questions of 3I Atlas, while it is close enough to answer. In the next part, we will look at a number that has stunned comet experts, the way this thing brightens almost twice as fast as any ordinary model can explain. Tails and strange orbits are already enough to earn 3I Atlas a place in the record books, but its brightness is telling a story of its own. When comets fall toward the sun, they usually follow a predictable script. As they get closer, more ice turns into gas, more dust is kicked into space, and the whole object brightens in a way that tracks its changing distance. It is not perfectly smooth, but the overall pattern is simple and comforting. Astronomers often describe this pattern with a power law. Take the distance to the sun and raise it to some exponent. That says how sensitive the comet is to heating. For most long-period comets from our own outer cloud, that exponent falls between about 2 and 4. Double the effect of the heating, get a reasonable increase in brightness. Nothing too dramatic. 3i Atlas does not like reasonable. Measurements from places like Lowell Observatory and the United States Naval Research Laboratory suggest that its brightness is rising as if that exponent were closer to 7.5. That means small changes in distance to the Sun produce huge jumps in luminosity. It is the difference between slowly turning a dimmer switch and flipping on a stadium floodlight. What could make a comet respond so violently? One idea is that this object is packed with super volatile ices. Instead of mostly water, it could contain large amounts of frozen nitrogen, carbon monoxide, and other compounds that begin to boil off at much lower temperatures. As sunlight reaches them, they do not just smolder. They erupt, driving powerful outflows that drag dust and produce a coma far brighter than any water-rich comet at the same distance. Another possibility is that the nucleus is cracking and fragmenting. When a comet breaks apart, fresh, bright material is exposed, and the effective surface area jumps. That can produce sudden surges in brightness, even dramatic flares. We have seen famous comets disintegrate this way, briefly dazzling before fading into debris. Yet the pattern for 3i Atlas does not match a single catastrophic breakup. Instead, it looks like a sustained, steep response, more controlled burn than one-time explosion. The result is a tension that astronomers can feel in the data. Either this object is made of substances and structures far more extreme than we usually encounter, or something about the way it is shedding mass and reflecting light is being driven by processes we do not yet understand. In the next part, we will step back even further and place this visitor alongside the only 2 other confirmed travelers from other stars, to see how all 3 together are quietly rewriting the rules of what a comet can be. To see how strange 3i Atlas really is, we have to remember that it is not our first visitor from another star. The story started with Oumuamua in 2017. That object was tiny, elongated, and tumbling, with an odd non-gravitational push of its own. It had no obvious coma, no bright tail, and yet its orbit would not fit gravity alone. It arrived, confused everyone, and slipped away before we could really figure it out. Then came Borisov in 2019. This one looked like the universe trying to calm us down. It had a classic cometary appearance, a coma and tail, and behavior that fell closer to what our models expect. Many astronomers breathed a quiet sigh of relief. Maybe Oumuamua was just a weird outlier, and most interstellar objects would be simple variations on comets we already understand. 3i Atlas has smashed that comfort. Instead of being a middle case between the 2, it pushes in a new direction. It has a huge active coma, a 5 million mile tail, and that unnerving anti-tail ramming toward the Sun. It shows strong non-gravitational acceleration like Oumuamua, but with far more visible activity. Its brightness jumps nearly twice as fast as our standard curves predict. And then there is the highly precise encounter with Jupiter Gravity Zone waiting in the near future. With a sample of 3, every new object feels like a new rule rather than a small exception. That is why the scientific conversation around 3i Atlas has such an unusual tone. A small but serious minority is willing to say the quiet thought out loud and ask whether any of these properties might hint at something engineered. They point to the focused jets, the efficient-looking acceleration, and the suspicious timing of the Jupiter approach. The majority response is more cautious but no less fascinated. Most experts still expect natural explanations, arguing that we have barely begun to explore the chemistry and structure of bodies born around other stars. In that view, Oumuamua, Borisov, and 3i Atlas are 3 points on a vast map we have only started to draw. The only way to know which story is right is to collect more data, from this object now and from the next wanderer that surprises us. By now you can feel the weight being piled onto this one short window in December. It is tempting to imagine that a single night of data will suddenly reveal whether 3i Atlas is natural or artificial. Reality is more subtle. What December really offers is a set of very specific tests, each one capable of killing bad ideas or forcing us to upgrade our models. It is less like a courtroom verdict, and more like a series of hard exam questions for the universe. First come the chemical fingerprints. When Hubble, the James Webb Space Telescope, and big ground-based observatories spread the comet light into a spectrum, they will see bright and dark lines tied to particular molecules. Strong signatures of water vapor and common comet gases would lean toward a natural comet with an extreme but familiar recipe. If instead the spectrum is dominated by very unusual compounds or by emission patterns that do not match simple sublimation, then the natural picture has to stretch. Then there is the speed question. By tracking how quickly material moves through the coma and along the jets, astronomers can estimate exhaust velocities. If the numbers line up with gentle boiling off of ices driven by sunlight, that supports the idea of intense but purely thermal outgassing. If they are consistently higher, edging into the range of chemical rocket plumes, and higher still in any region that would hint at an ion-like flow, the argument that this is just a wild snowball becomes harder to defend. The December campaign also pins down the orbit with ruthless precision. Every new position measurement before, during, and after closest approach helps refine how strong the non-gravitational acceleration really is, and how it changes over time. A smooth, slowly varying extra push is exactly what you expect from natural jets that wax and wane with sunlight. Sudden shifts or carefully timed changes would be far harder to explain without intentional control. Finally, if we are lucky, high-resolution images will give us hints about the nucleus itself. Even a rough estimate of its size and shape will plug into models of mass, density, and spin. Combine that with jet strength and orbital drift, and you get a much clearer sense of whether the numbers balance for a natural comet or keep pointing toward hidden engines. By the end of this observing window, we may not have a headline that says, "Mystery solved," but we will almost certainly have a sharper picture of which explanations still stand and which have quietly died under the weight of real data. In the next part, we will zoom out from this single object and look at how 3i Atlas is already changing the way we hunt and study future visitors from the stars. 3i Atlas is not just an object in the sky. It is a stress test for how quickly humanity can react when the universe drops something unexpected in our backyard. Think about the timeline. Discovered in July 2025. Closest pass to Earth in December of the same year. A brush with Jupiter gravity bubble in March right after. For big space missions and slow funding cycles, that is almost no time at all. Yet the response has been anything but slow. Survey telescopes that scan the sky every night raised the first alert. Within days, orbit calculators flagged the hyperbolic path that marks an interstellar object. Observatories in different countries began to trade data almost in real time. Professionals booked precious nights on major instruments. Dedicated amateurs pointed backyard observatories and half-meter telescopes and contributed measurements that genuinely sharpened the orbit. The whole system of modern astronomy snapped into a higher gear. We have seen hints of this before with Oumuamua and Borisov, but 3i Atlas is the first case where the community had months instead of weeks, and where the object was bright enough for a truly global campaign. Software that hunts for moving dots against star fields has been upgraded. Automated alert systems are being tuned so that the next suspicious track gets flagged sooner. Schedulers for space telescopes are learning how to carve out emergency observation slots when a once-in-a-generation target appears. There is a deeper motivation behind this scramble. Astronomers are increasingly aware that we are probably seeing only the loudest visitors. Bright, active, comet-like bodies announce themselves with huge comae and long tails. Darker, quieter objects could be slipping through the solar system right now, reflecting almost no light and leaving almost no trace. For every dramatic 3i Atlas, there could be dozens or hundreds of interstellar rocks and dormant comets passing unnoticed. That is why this campaign is about more than one object. Every trick developed to study this visitor can be reused. The spectral setups, the tracking routines, the data pipelines, the ways space agencies talk to amateur networks and share results with the public. All of that becomes part of a growing playbook for the next time we catch a messenger from another star. In that sense, 3i Atlas is both a mystery and a rehearsal. Whatever we learn from its wild behavior will reshape how we watch the sky, how we classify what we find, and how quickly we can turn curiosity into coordinated action. In the final part, we will widen the frame one last time and look at what it really means for our species to be reading the chemistry and motion of matter that was born around another sun. In the end, 3i Atlas is more than a strange light in the sky. It is a piece of another star system that has wandered into ours and allowed itself to be measured. Every atom in its ice and dust was forged in a different furnace, under a different sun, in a place we will never visit with rockets or probes. Yet here it is, letting us read its chemistry and its motion across the black. That alone is astonishing. Think about what this object has already forced us to confront. A tail 5 million miles long and a sharp anti-tail that seems to fight the solar wind. A brightness curve that explodes far faster than our comfortable models expect. A steady non-gravitational push that hints at powerful jets or something more efficient. A future path that threads the edge of Jupiter gravity domain with surgical precision. None of these facts by itself proves anything exotic. Together, they paint a picture that refuses to be boring. There are two honest ways this story might bend. One path says that 3I Atlas is a comet, but a comet from a very different neighborhood. Packed with super volatile ices sculpted by collisions and stresses we have never seen, behaving in ways that stretch our idea of what natural can look like. If December and March point that way, the result will still be profound. It will mean that our solar system is only one small example in a galaxy full of much stranger chemistry and physics. The other path is harder to talk about, yet impossible to entirely dismiss. If the jets move too fast, if the acceleration is too clean, if the structure of the nucleus or the choreography of the orbit continues to look engineered rather than random, then we may have to consider that we are watching technology rather than geology. Not because we want that answer, but because the data leave us nowhere else to stand. Either way, this is what real science looks like. We notice something odd. We gather every scrap of data we can. We argue, we test, we throw away bad ideas and keep the ones that survive contact with reality. You are living through that process in real time, not reading the summary years later. So as 3I Atlas races past Earth, swings by Jupiter, and then climbs back into the dark between stars, we watch, measure, and wonder. Maybe it will leave us with a neat explanation. Maybe it will leave us with better questions. Both outcomes are victories. They mean we are doing what our species does best. Looking up, refusing to be satisfied with easy answers, and letting distant worlds write their stories in our skies.